Hello everyone, my name is Furkan. I work at Autodesk. But I'll skip the boring part because this is something that I've been meaning to talk about for a long time, because this is a solution that we implemented for our product, like 5-year project. It's a gigantic legacy system that we have to deal with. And this is something that helped us tremendously, reduced a lot of code load for us. And I've been looking forward to finishing the project so I can finally get to talk about some of the cool things that we did during that time. And this is among them. So just as a prologue to the solution, we started the project. There was 6-7 million of lines of code, all of it legacy. Some of them hasn't been even touched in 20 years. And one of the constraints that we had for the project was that we can't change any of that, because if we go into it, it's going to be side effects, it's going to be things that we don't really touch for the scope of the project that we're going to work on, because it's supposed to be a re-architecturing of the system only for GUI purposes and replacing the UI toolkit and basically doing something, replacing it entirely and do something from scratch. And two things that I need you to remember is the data that we transfer from the core side, the non-GUI related side, to UI side are called symbols, which are similar to the properties, Q properties. And the thing that contains all of these symbols is called symbol table, which is just essentially like a std map of Q properties. You can think of it in those terms. They're going to be very similar. But it provides a lot more over that, which are irrelevant for this talk. Data representation in the core, this happens in thousands and thousands of places, so this was something that we couldn't change. It declares symbols, integer string, or function symbols that contain lambdas inside, or in the past it contained function pointers. And then this information makes its way up to the UI at some point, and then whenever the core side changes internally, it can notify the users of these symbols so that they can also represent that state change in the GUI. And this is generally used for any type of data that represents UI. It might just be number, it would just be maybe the radius of a geometry shape that we have, or the number of vertices that we have. All of these, no, the number of vertices are not related to this, sorry. But all of the GUI-related things are represented with these, and the way that we create the UIs, you'll see that this is also a very imperative style that's been used since the 80s in the code base. And it essentially declares we call it a control box, gives it a title and a few other properties to declare how it's supposed to look like, and then adds these controls that are just displayed from top to bottom. The initial attempt when we were doing the project was the imperative style, where we were like, we have all this data, it needs to make its way up to the UI somehow, so let's just have a lot of virtual interfaces. C++ is an object-oriented language. Virtual interfaces are great for these purposes. So we had a core editor that contained some of the core functionalities that only the core side access, because we didn't want the core access in the GUI side in any way. But the GUI side could reach down when it was needed. And this one was declared in the core side, and then in the UI side, in the quick side, which we called the QQml layer, we had multiple virtual interface, multiple classes that inherited from this, so that it can add additional things that it needed to display data in the UI, or open window, close window, and various other things. And if we look back here, you'll see that we also have addInt, addString, and there's many other forms of this. They needed to make their way up to the UI somehow so that we can display the correct form of these controls. An integer could have a text field and a slider, or a stepper, whatever that may be. And in those cases, the initial attempt was to have a control base that contained some of the common properties of all these symbols, and then on top of it, there were specializations of it using different names, like control and control string. All of these would provide different ways of accessing that data. So code for that would look something like this. Each editor had a lot of data. Like in our editors, there are some editors with millions and millions of rows, but because it's representing data from a 3D model with millions and millions of data points. Would you mind? Thank you. So the basic form of it would look something like this. It would get some data, open the window, set some data from the core, because they would be virtual interfaces in some cases, and it would create those control base instances and then expose them as a list of control bases so that QML side can access and then put it in a repeater or do whatever it wants with it. But in some cases, we needed additional information that can't be put into a list of rows. Maybe we want to show some icon somewhere, some view somewhere. In those cases, we use dynamic properties that were created from the code that we see here, this add integer stuff, and then it would make its way up to, pardon me, can you press once more, thank you. Up to here, which then it would process all of that information and unconditionally expose all of that data using QQmlPropertyMap. The control-based version of it would look something like this, where we have, for color purposes, we would have a triple symbol that would contain just an array of 3 numbers to represent color. But since we can't really expose that, we had to have abstractions over that with QObject so that we can expose that somehow and then expose them as properties so we can access them. And in the QML side, we would have this. In multiple places, we would have a repeater with whatever view that we're using. The model would come in as controls. There's this loader. It has some decision-making process there depending on the incoming data. Is it a control base? Is it a control int, control double? It would use a different component for those cases. But since we cannot really expose that control base as a different type because it's being used as in a repeater, we had to declare it as a var property and then move on from there so that Qt can do its introspection and then see which type that is. And when we needed something custom, we would use the dynamic properties, but that means we have to get into individual places where we know what we need, and then that process, QQml property, also works very slowly. And since, remember back to the time when I said we can have multiple symbols, also function symbols that can either contain lambdas or function pointers. What happens when we need to expose that? We should just put that in a symbol in the class, expose it as a QInvocable, and then internally call that. Or call some internal virtual function, some protected function underneath the inherited class so that something can happen, whatever that thing is. But if you want to expose more things, which we ended up doing as the complexity of the project increased, then you would end up with multiple of these. And one of the developers abbreviates function as a fun, so that's why I said not fun, if you have a lot of those things. So the cons of this, I'm sure it's very obvious by now. It's not something that you want in your project, especially as the complexity of the project increases. You'll have a lot of code load. You won't be able to rely on static types, so you're going to end up guessing what you're using by the time those things are instantiated. Each change that you're making, let's say you're building an editor that exposes just a title and an icon and a list of controls. But the UX comes in and they're like, you know what, we already have these things here, how about we expose that too? Especially if it's a prototyping situation, you have to change that code, rebuild it, and then launch it again to see what's going on. So every change required a rebuild, which is not fun when you're dealing with, especially during the early stages of the project where everything was changing pretty fast. We needed to prototype pretty fast as well. And that's one of the reasons why we implemented QML live reload so that we don't have to do any of this stuff. And every function call, again, the importance of these function symbols is that we don't want to be putting more code in the quick layer, QQml layer, than we have to. From the beginning, we only intended to use QQml for GUI purposes only. So we don't use any of the lab modules and whatever other add-ons that they have. We try to stay away from it because we mostly don't have any need for it. We only need QQml for the GUI purposes. So what we realized at the end of a few months was that this sucks. We have to find something else. But we needed to have other realizations to get to a good solution. And those realizations were that we have way too much boilerplate to expose to these, have to write a lot of boilerplate code to expose these data. Our data, if we remember back to that symbol table, is essentially like a JSON object where we have the the key and the value pair in a way. And virtual interfaces created dependencies that we didn't enjoy. We would much prefer that we can just sever a connection, and in that point, the core and the GUI don't know about each other, but the application still lives on. Maybe we want to import another state from a JSON file or from the network and then show something else. And maybe you want to run a shell of application for GUI GUI testing purposes or prototyping customer feedback purposes without all of the baggage that we bring in underneath. with all the graphics and geometry and all that stuff. And this was, the symbols we add might be needed, might not be needed, but with the previous version, all of them were exposed unconditionally. Whatever you put in that table were exposed, especially in that QQmlPropertyMap. And one of the things, is anybody familiar with Redux Flux architecture for data management, data state management? For that, the main idea is that you want to control when a change in the state happens, so that you can basically trace back your steps and then even recreate different events in your architecture. So it's kind of event-based and kind of declarative-based. Changes happen at certain points. Singular places are responsible for changing or propagating the effects of it, which makes it somewhat easy to understand how things are changing. And this was something that we wanted as well, since we were modernizing everything. And the solution, this is just the final result. I'll go back into details. This is what we had in the beginning as well. We have a symbol table with multiple symbols. There's a lot more different types that we're using, but some of the basic ones are this. And we even have a function symbol that we want to call from the QML side when somebody clicks a button, right? The QML representation of it is, we have a new type called symbol table model. That was the first name that came to my mind. I still have a to-do right on top of it that says, find a better name for this. I haven't been able to. This symbol table model says, some information is going to be exposed to me. And in that information, I'm only interested in these things. And I know what the types are. So if you receive any other type other than this, then we right now assert, and you can have other error handling mechanisms depending on your needs. And we even have a function there, which I'm realizing now there's a syntax error, but we can even do a function where you can just call, and then it'll call into the core with where all the complexity happens, and you don't need to worry about it. And if you run this code, you'll see that all of it prints the values that we put up there, and then the Greek function call will be a JavaScript function object that you can call, or even you can do the other fancy JavaScript stuff where you can pass it on to something else or bind some other object to it. Also, your docking question, this might help because this is a docking implementation. Can you play? I think there's a play one there that you can reach. Oh no, we can't reach that. Anyways, it would have been fun to see. Oh, okay, that works. So this is a complex example. I misremembered, there's no docking here, but there's some flexible UI happening. You'll see that in the middle, when we're listing all the shaders, there could be 10 shaders, 20 shaders, thousands of shaders, depending on the company that's using this. And on the left, you see another control that we have, an editor that we have, but it has a lot of these things like checkboxes and multiple other things. And we have another editor called information window, which will contain all the information that you need for a model, which will have millions of rows, right? No. Okay. So for the example of the shader balls in the middle, here's the data that we need for it. The width and height, some draw layers we use. We implemented some way of layering multiple OpenGL calls. We didn't support it internally, but we did some tricks on the QML side to do multiple draws on top of each other to make things more performant. And the draw layers represent what needs to be drawn in that little rectangle that we have. And the items are, do we need additional items in there for maybe changing the color, adding additional things to that shader ball that will contain that. In the mouse table, this is actually something that we use to expose, for example, event data back to the core. So this is not just about exposing things from the core, but also exposing things from the UI side back to the core. I think there's another click here. Oh, there isn't. And another example, this is an example, a base example for the controls that we have, the control in, control double cases, where we only expose these things, but there could be more underneath. But if we need more or less, we can change it, but we don't need to do any recompilation. The designers don't even need to. Actually, in our project, for example, we did a lot of training for designers. They write code base, our onboarding window designed from scratch and coded from scratch by our designers. And she didn't talk to me the entire time, which was really nice, even though I love her. At the end of it, she just showed me the code and then created a PR for it. And when she needed data, she just looked at other places that she had experience, and she was like, oh, like these things are exposed, I don't need them, just remove them from there, and then just use these things, which makes things easier to understand because I don't need noise, right? The signal here is that I need the title and the type, not everything else. But if we needed more, then you could add more things to it, and then maybe you'll have some, if that data doesn't already exist, some developer intervention there. But most of the times we have a lot of things that we're not exposing that designers know and then just add it, or even developers know, they'll just add it and it'll work. I think this is the last one. Oh, sorry. 3 times. Thank you. So when we expose these things, no code change in the C++ side is needed. And another cool thing with this is we can play with the types that we're exposing, so we can expose these data in more creative ways. One of the ways that we did is that when you have that view information that I showed from before with the height and draw layers, if we have this in some other top layer data, you don't need to be like, go into this, fetch this, and move it into that, into this model what I declare. You can just be like, oh, you're going to have another table that contains these, so I'm just going to give you a simple table model, internally deal with that complexity that I don't need to know about, and then give me this information. And another thing that we have, this is a control table list that we use to display all those controls from top to bottom, but there are cases when you click a button, something disappears or something shows up, right? And in those cases, we use the sort proxy model, QSort proxy model, to filter those out. But in here, again, you don't deal with any of that complexity. You just say, I have these controls that will have this sort of behavior, so create a type for me that provides that behavior, and then I'll just use that. Which this can also provide other things for you that you can use in a more declarative way, or maybe you have some imperative style needed that's buried down somewhere that nobody needs to see, and then you can access the interface, like invocables or properties in here that you can do a lot more with it. So how does all this work? When something in the symbol side, in the core side changes, it first notifies the symbol table model. Again, this is a one-way information flow, and we know exactly where that information is flowing from and to. And from then on, that symbol table model, it knows what properties are declared inside. We cache all of this information in beginning, so you don't have to look all the time, and so there are a lot of optimizations underneath. And that updates the property for the QML side. QML reacts to changes, and then maybe it decides to change some other things, some other place. Then all of that makes its way back to the symbol table model, and that decides what to do with it. It either notifies the symbol does something else, depending on the type information, the property type that you've declared. Oh, there's no. This is, I couldn't show a lot of information. This is internal code, but this is the basic interface of it. We have some map of symbol bindings and table bindings, and another cool thing that I forgot to mention is we can actually expose signals with this as well. So in the core side, we push an empty function symbol, a no pointer function symbol, and then on the QML side, we declare a signal. And this symbol table model knows what's declared inside, right? Are they functions, are they properties, or are they signals? And whenever that function object is triggered, we get notified for it, and then invoke a signal on the QML side. So you can even invoke QML signals all the way down from some core side that has no idea that QML exists. And those property and method caches are used for that purpose. And the symbol table is the one that contains all that information. Other cool things that happen underneath is this. The other ones are essentially just wrappers over what type of data we're dealing with. Is it a table so that we can do more fancy things? Just a symbol property, then we can deal with that. Property binding base provides some of the common things, but there are different ways that we handle things that we had to add additional classes to handle. But the QML function symbol executor is the interesting one that enables us to call a function in the QML side and then have that call a function in the core side. And the way that works is I will have some clicks here actually, just to highlight it a little bit. It only works for function symbols. It gets the QML engine that the symbol table was declared in, so we're not dealing with anything else. And this bit creates a function that returns another function bound to the object that we're passing in the function that we're calling. So if you look here, this object is passed into the bind call here, which binds the context of the JavaScript function so that when we call this, it refers to the object so that we can do a call into the QML function executor, which then internally takes care of all the arguments, even does type checking in there so that we know we're calling with the right number of arguments and with the right type of arguments. And the next part is just a way to execute that briefly so we can get the final function object that can be passed on to the QML side. And what the call function looks like is it gets a list of arguments because that's what we're providing in the QML side, puts them all into a list that the function object will consume, and then invokes that. We even have support for returning things from that call that goes into the core. So if you're doing some calculation that needs a result in the QML side, you can even do that, return something, or you don't need it, then do it maybe asynchronously. You don't need the result and don't care at all. It provides a lot of flexibility for you to deal with these things. So where do we go from here? Because right now we've been using this solution for about 3 years. We haven't run into any performance-related problems. There are some problems with debugging some of the information that we declare there. That's still we're working on that because of the dynamic nature of it. Sometimes we have a typo in there that's hard to see. Sometimes we miss it. But since we know the connection where data is coming from, at least you can look at the model, look at the data that we describe in the core side, and be like, okay, we have a type mismatch. Type mismatch is reported already, but you can see the changes. We have other logging capabilities implemented so that if the property that you declare doesn't exist in the table, you get a log or an error. If the type doesn't match, you get an error. A lot of nifty stuff like that. Next thing that we want to look into is how QML compiler extension works with this, because we are essentially declaring all of that in a type-safe way in the QML side, but I didn't yet get a chance to look into how the QML compiler will act with that, whether or not it'll be faster, slower, or whether or not we'll run into any problems at all. That I don't know about. That we'll look into at a later time. And the other one is making inspection and debugging easier, but there are ways of providing custom QDebug calls so that when you're logging something, it'll essentially maybe dump out a JSON object, so we tried that. But definitely, the ergonomics of debugging could be much better there. Thank you very much for listening again. If you have any questions, let me know.
How do you deal with autocomplete? For example, if you expose a property in a QML, how do you know which property you're
That's the beauty of it. If you have proper QML tooling enabled, then what you declare there, it'll just show up in some other place they're using because it is in the QML code, right? You'll see.
It is. But how do you know the property name? For example, if you expose a C++ object, right, and you have a property, and the property is height. When you actually write in the QML code, you get the access of the exposed C++ object, press dot, height, autocomplete, you know that's it.
We're not actually exposing the C++ objects. That symbol table that you see there is never exposed. What we expose, what you know about, is the symbol table that declared properties. That you can just open that QML file and see what properties are there. So we don't run into that problem.
But you have to open the file to see the properties of it.
No. If you have autocomplete enabled, like if you're using Qt Creator, you do model dot, it'll show you all the properties, right? Because they're not somewhere underneath where you need to do some additional tooling to expose that to a QML types file so that Qt Creator can read it. None of that. It's directly inside a QML file so that Qt Creator can just read it and complete all of that for you. Thank you.